6.3. We are starting what is called systems of equations. And in this class, we're only going to do systems of linear equations. So we've spent a lot of time graphing lines, looking at the graphs of lines, solving linear equations. Now we're going to include two equations at the same time. So let me pull up our ALEKS assignment. Maybe. All right, here it is. So here we have two linear equations, and we're being asked, is 4, 1 a solution to this set of linear equations? What that wants to know is, if I put 4 in for x and 1 in for y, do I get a true statement? So 1 is equal to -2 times 4 plus 9. Is that a yes or a no? That's a yes. So are we done? We actually have to plug it into both. What? Okay, so does this work in here? Yes. What does that mean graphically? It's a solution. And graphically, what does that mean? No. So this is the equation of a line, but when I plug a point in and it works, what does that tell us? That point is on the line. Does that make sense? So I now know that 4, 1 is part of the first equation. But that's only half the story. I need to know, is that point also part of the other equation? So I plug 4 in here and 1 in here. And I get 4 times 1 plus 2. Oh, that's not what I wanted. 4 times 4 plus 2 times 1. Is that equal to 18? 4 times 4 is 16. 16 plus 2 is 18. So yes, this point works in both equations. Right. Yep, it has to work in both. So let's try this. 6 and 0. 4 times 6 plus 2 times 0, is that equal to 18? No. Do I need to try the other one? Nope. The answer is just no. Okay, let's try 5 and -3. 4 times 5 is 20. 2 times -3 is -6. Is that a true statement? No. So that did not work. So 4 times -5 is -20. And 2 times 19 is 38. Is that equal to 18? Yes. Now I need to try the other equation. Put 5 in there, 19 in there. Is 19 equal to -2 times -5 plus 9? Yes. Wait. I did something wrong. I should. Oh no, we're good. We're good. So yes. Okay. Okay. this over. So, when I graph two lines, what can that graph look like? And it turns out there are only three possible outcomes. Here they are. Okay. We could have two lines that intersect once, like this. We could have two parallel lines that never intersect, or what's going on here? It's one line right in the exact same spot as the other. Okay? Now, mathematicians like to do this funny thing called consistent, dependent, inconsistent, whatever. That's not really important. Sorry. But I couldn't find a problem that did anything differently. So, what you need to know is this first one says infinitely many solutions. How many times do those two lines touch? They touch in an infinite number of places. Okay? How many times does the second one touch? Once. So we click on that, and then we put the solution. So we would write -1, 0. And then how many times does the third one intersect? No solution. Okay? That's the important part. All right? But we have to match those up with the other equations. So if they don't touch, it's inconsistent. And if they do touch once, it's consistent dependent. And if they touch an infinite number of times, it's consistent independent. Now, hold on. Let me check that so I don't... I don't want to lead you astray. So, -1, 0. Oh, what did I do wrong? Did I get these upside down? Okay. I was wrong. I got them backwards because nobody really uses these. So infinite solutions is consistent dependent. One solution is consistent independent, and no solutions is inconsistent. But once again, not a big deal, but you have to put those in there. Okay. Number 3. So graph this system. Yeah, graph them individually. So the first one, we start at -1, and then we go up 1 over 2. Right there. Oh, I guess I could have just done that. Okay. And the second one, when I cover the x, what does y equal? -6. I missed. Okay, -6. And when I cover the y, what does x equal? -3. Now, where do they touch? -2, -2. So I write -2, -2, and solve it. Okay. If they're the same line, we write infinitely many solutions. If they're parallel, then we click no solutions. Yeah, you just type in. Okay, use the ALEKS graphing calculator. Where is the ALEKS graphing calculator? Right there. Okay. Go away. It won't let me move that. So we click y equals, then we type in the equation, So negative 3 x minus 5. And then in y2, negative 10x minus 9. And when I have those in, I push graph. And then I figure out where they intersect. So I wish I could make this bigger. So I don't know if you can see that, but those don't meet at a nice number. Yes. So they don't meet at a nice point, but if we ask it to find the intersection for us, click intersect, and it wants to know what's the first graph, what's the second graph, and we want to guess an x. What does it look like the x is? Somewhere between 0 and negative 1. So I'm just going to touch right. I'm going to click negative 1. And why won't it let me? I can't move this. That's a problem. How do you move it? Let me try a mouse. I can't see the answer. Okay, there we go. So find intersection, and then it spits out these numbers. And the question says round to the nearest hundredth. How many decimal places is a hundredth? 2. So we're going to round right here, negative 0.57. And this one we're going to round here, and we have to bump the 8 up to a 9. So it'd be negative 3.29. Okay, so what you do is you type in a graph, you click graph. Oh, let's say. So you have two graphs, you push the graph button, and then you click intersect, and yeah, you look where they cross, which is right here, and that looks like x is about 3. So for my guess, I'm going to type in negative 3, click find intersection, and it will spit out that number, negative 3.5, 5.5. So it says guess point, x equals, so my guess is my x. And chances are you could guess something way off, and it gives me the same answer, because there's only one intersection. So the reason it's asking you to guess, if we had a more complicated graph that looked like this, and then another one that looked like this, that has 4 intersections. So the calculator wants to know which intersection do you want which one do you want me to find, and you pick the x values. Say, look around here somewhere, and it will figure that one out. But we're just graphing 2 lines, so they can only touch once. And so it probably doesn't matter what you guess, the calculator is going to find the answer. But if there's more than one intersection, then when you type in your guess, it will find the closest one to that point. Yeah. Go to y equals, and then type in the equation. Okay. Number 5. Oh. Okay. Oh my goodness. Sorry, guys. There we go. Now we can go on to number 5. Yeah. Okay, this is a little bit harder. We have to use the graphing calculator. What's wrong with these equations? Well, there are nasty decimals in there. What else is wrong with them? They're not in y equals form. So I have to get the y by itself. So if I take 5 minus 0.7x equals 0.2y, how do I get y by itself? Not multiply. What's holding the 0.2 and the y together? So divide by 0.2. So divide by 0.2. That's one equation. What about the other one? I'm going to add y to the right side. What else do I need to do? So this goes away. So now I have 0.4x equals 4.3 plus y. I need to subtract the 4.3 to the other side. So those are my two equations. So I go in. Yes, and then we just do the same thing. But once again, I can't grab the calculator. So we do this from the computer. All right. So y equals. Okay, now the first one, I need to put parentheses around it because it's the top half of a fraction. So 5 minus 0.7x. And then I want to divide that by 0.2. And then the other one is just 0.4x minus 4.3. And I click graph. And then I click trace. And for my guess, I just need to type in a number that's somewhere close to this point here. So I'm going to just type in 8. Find the intersection. Then I round to 2 decimal places. And that's it. Yep. 2 hours apiece. Okay. Get to work.